Imagine something in the sky so vast, so monstrous, that it makes our mighty sun look like a single glowing grain of sand in an endless desert of space. Think about this. If you replaced our sun with this object, it would stretch all the way past Mercury, Venus, Earth, and keep going. Mars, engulfed. Oh. Jupiter, gone. Even Saturn, hundreds of millions of kilometers from the sun, would be swallowed whole. No, this isn't a science fiction story. This thing is real. It's called Stephenson 218, the largest star we have ever found. Here's the part that has scientists scratching their heads. It's so big, it shouldn't exist. Now, we're not just talking about big like twice as big as the sun, we're talking over 2,000 times the size of our sun. That's not just big. That's astronomically impossible, or at least it was supposed to be. So how did something like this form? What keeps it from simply collapsing under its own enormous weight, or exploding in a titanic burst of cosmic energy the size of a galaxy? The size of a galaxy. The bigger question, what does something this massive mean for us, for physics, and for our understanding of how the universe works? In the next few minutes, we're going to take you on a journey through light years, through questions so large that even our most advanced computers only guess at the answers. We'll travel into the depths of the Milky Way, into a star cluster that's home to monsters, giants, and one star that redefines what's possible. This is not your typical story about a star. This is a look at the limits of the universe, and Stephenson 218, it's sitting right on that edge, staring back at us. But first, let's back up. Look up at the night sky. You might see a few hundred stars if you're lucky. If you had a telescope, a good one, you'd see thousands. But with the tools we have today, radio telescopes, infrared observatories, space-based eyes like Hubble and James Webb, we see not hundreds, not thousands, but hundreds of billions of stars, filling up our galaxy like grains of sand along a beach, and almost all of them follow the rules. Nearly all of them live, shine, and die in ways that our physics can explain. Birth, life, death. Stellar nursery, main sequence, red giant, supernova. It's a cosmic dance routine we've come to understand. We have formulas for it, predictions, timelines. But every now and then, something refuses to follow the music. Something so monstrous appears, it wrecks the choreography. Something like Stephenson 218, a star so big, so unfathomably strange, that it completely breaks what we think we know about how stars form, live and die. Scientists knew there would be massive stars, sure, but nothing like this. Discovered in the 1990s, but only fully understood recently, Stephenson 218 sits nearly 19,000 light-years away from Earth, buried deep within a thick cloud of dust and gas in a star cluster known as Stephenson 2. The cluster itself isn't small. It's already packed with red supergiant stars, twisting and pulsing with dying heat. But 218, it's different. Astronomers at first couldn't agree whether they were looking at a single object or a nebula, a massive field of dust reflecting light from somewhere else. It was just too faint, too spread out. But then they noticed something. Among all the stars in that region, one signal pulsed louder than the rest, hotter in the infrared, stretching wider and longer than anything they could explain. The measurements didn't lie. The farther they zoomed in, the more terrifyingly huge this object became. Not a nebula, a single star. Yet, despite its enormous size, it's not especially bright in our night sky. And here's why Stephenson 218 is dying. It's a hypergiant, a monster of short life and explosive death. It's red, it's bloated, and it's on its last breath. But even as it fades, it teaches us things. Big like the entire foundation of stellar physics might be flawedy kind of big. Because this star, it simply should not be holding together. According to our understanding, gravity should have pulled this thing apart long ago. Or it should be shedding mass like insane, and to be fair it is, but somehow it's still here, still intact, still observable. That's like watching a snowman survive a volcano. It's not supposed to happen. So, what exactly is Stephenson 218? Well, to understand it, we need to understand what it means to be a red hypergiant, and why these stars live so fast and die so violently, because this isn't just a star. It's a cosmic clue. The kind that might lead us to better understand how stars die, how black holes form, and what we haven't yet discovered about the laws of the universe. As we dig deeper into its story, keep one thing in mind. If something this big can exist, what else is out there that we haven't even seen yet? Because the deeper we look into the universe, the more we realize we're not just small, we're still learning the rules. Let's rewind to the moment it all began. Not for the star itself, but for us, the observers. Buried in the data of infrared telescopes back in the 1990s, an astronomer named Charles Bruce Stephenson was conducting a survey of bright, red celestial objects. These weren't visible through ordinary optical telescopes because their light was obscured by interstellar dust clouds, but in the infrared spectrum, they burned brilliant and massive. Stephenson compiled a catalogue of potential red supergiant stars, most of them obscured, distant, and relatively unknown. This catalogue became what is now referred to as the Stephenson 2 cluster, a star family tucked away deep in the Milky Way, some 19,000 light-years from where you and I stand right now. But what scientists didn't know then is that one object in that catalogue would change the game entirely. It didn't even stand out at first, Stephenson 218. Just one number, one name among hundreds in a long list of red giants, wasn't waving a red flag. Its visible light was faint, swallowed by thick cosmic dust. Its presence, a whisper in the blackness, but astronomers kept coming back to it. The numbers weren't adding up. The star was, somehow, brighter than expected in the infrared. Its light curve stretched across more of the sky than it should, and its size that became the problem. When they tried to measure its radius, the first numbers looked like mistakes. It must be a misidentified cluster, thought some. Maybe even a nebula shining with borrowed light, not a single object. Couldn't be, wouldn't make sense, but it was. As observations improved, especially with the help of powerful instruments like the Very Large Telescope in Chile and infrared data from space-based observatories, they began to realize Stephenson 218 wasn't a nebula, it wasn't a cluster. It was just one colossal star. Now, picture this. Imagine you're looking at a streetlight from 20 miles away. It's dim, hardly visible through fog, but you're using a special lens that can only pick up heat. Suddenly, the lamp looks massive, and it's glowing far more than it should. That's how astronomers were seeing Stephenson 218. Not by what it looks like in visible light, but by the sheer heat it was throwing off in the infrared. They had discovered something truly rare, a red hypergiant, a stage of stellar evolution reserved for only the most massive stars. Not just supergiants, hypergiants. These stars were on their deathbeds, shedding mass like furious fireworks as their cores melted heavier and heavier elements in desperation to survive. And yet, nothing in the textbooks prepared them for this. Stephenson 218 wasn't just big. It was astronomically impossible. According to their calculations, its radius was somewhere between 2,000 and 2150 times that of our Sun. To give that number meaning, let's do the thought experiment. Remove the Sun from its place in our solar system. Now, insert Stephenson 218 in its place. Its edge would reach out past Mercury, past Venus, past Earth, past Mars, past Jupiter, even past Saturn. The limits of the star's surface would stretch to somewhere near or beyond the orbit of Titan, Saturn's largest moon. That's not a star. That's practically a solar system in itself. Its volume, you could fit over 10 billion suns inside of it. And keep in mind, our Sun already holds more than 99% of the entire solar system's mass. And here's where the paradox begins, because according to our understanding of how stars work, that shouldn't be possible. A star that large should have lost so much mass through radiation pressure and stellar winds that it would collapse, split apart, tear itself into pieces, or explode long before reaching such a size, or, at the very least, shrink down from such extremes as its internal pressure gave way. But Stephenson 218, it just sits there, glowing, pulsing, refusing to behave. It's one of the brightest infrared sources in its region, and yet all we can see from Earth is a whisper, a dying ember in a dusty corner of the galaxy, putting off enough radiation to outshine entire star clusters. And still, for decades it stayed in the shadows of space, hiding behind distances so incomprehensibly vast that it might as well be a dream. But it's very real. It was declared the largest known star, even larger than previous record holders like I-Scuti and Westerlund 126, both thought to be cosmic giants. Those stars broke the scale, but Stephenson 218 shattered it. And it left astronomers with a difficult question. Could we be wrong about how stars work at the highest extremes of size and mass? Perhaps the assumptions built into our models, equations of mass, temperature, luminosity, no longer apply in this strange domain of superstars. Perhaps in this murky area of stellar evolution, we're missing something fundamental. This is the moment when science becomes more than fact, it becomes exploration. If Stephenson 218 exists, and if it behaves as the data suggests, then it becomes a portal to new knowledge. A clue ripped straight from the hearts of dying stars, because somewhere in its 2000 solar radius belly, something extraordinary is happening. This star isn't just challenging models, it's begging us to rewrite them. So now the bigger question isn't just how big this star is, it's how. How does something this enormous even hold together? How did it form? How long will it last? And when it dies, what happens next? That's the journey we'll take you on next, because when you're dealing with the largest known star in the entire observable universe, there are no small questions. Let's take just one moment to pause and really take in what we're dealing with here, because saying a Stephenson 218 is over 2,000 times the size of the Sun sounds impressive, but it barely scratches the surface. Let's break it down visually. Imagine the Sun sitting where it is now. Nice and round, burning hot, 109 times wider than Earth. If the Sun were the size of a basketball, Earth would be a grain of salt orbiting several feet away. Now scale that up. Stephenson 218 isn't just wider than the Sun, it absolutely dwarfs. If the Sun were that basketball, Stephenson 218 would be the size of a football stadium, maybe more. And what's terrifying is this: if Stephenson 218 replaced our Sun, its surface would extend beyond Saturn's orbit. Not Saturn itself, the orbit of Saturn. That's nearly 1.5 billion kilometers. It's like placing a bonfire in your backyard and its flames reaching other countries. And then comes the mind melter. Light, travelling at 299,792 kilometers per second, takes over 8 hours just to cross from one side of this star to the other. To cross the Sun, just a little over 4 seconds. That means if this star winked out of existence right now, we wouldn't even see the far edgy turn offered for most of the day. When scientists say this star shouldn't exist, they don't mean it metaphorically. They mean it literally. According to physics, the math, the simulations, the carefully tested models of how stars live and die, a star like Stephenson 218 is not supposed to be possible. There is, quite literally, no stable equation in our current understanding of stellar evolution that comfortably explains how something of this size can form, survive, and stay intact, even temporarily. So, what went wrong? Let's start at the core of the issue: the science of stellar structure. At the heart of every star is a finely tuned balance. Gravity pushes in, fusion pushes out. In smaller stars, like our Sun, this balance lasts billions of years. The Sun is relatively calm, predictable, and stable, but in massive stars, things get chaotic fast. Once a star passes a certain mass threshold, typically around 8–10 times the mass of the Sun, its evolution starts to accelerate. The core gets insanely hot. Hydrogen gets used up quickly. The star then starts fusing helium, then carbon, then oxygen, heavier and heavier elements in layers like the rings of an onion. Each fusion layer is shorter lived than the last. By the time a massive star is fusing iron, it's less than a day away from total collapse. Everything speeds up in massive stars. Instead of billions of years, their lives are measured in millions, or even hundreds of thousands of years. But there's still a limit, or there was supposed to be. In every model of stellar growth, there's a point called the Eddington limit, a maximum luminosity. Beyond this point, radiation pushing out from the star becomes so powerful it actually overcomes gravity. It effectively blasts the star's outer layers away. So imagine a balloon that's inflating. If too much internal pressure builds, boom, the surface can't hold. The Eddington limit is that balloon popping point for stars. Every time a star grows too luminous, too large, or too unstable, it loses mass. Mass loss is the universe's way of keeping the cosmic books balanced, but Stephenson 218. It laughs in the face of this limit. Its luminosity, its sheer power output, is estimated to be over 440,000 times that of the Sun. That's crossing into Eddington territory, and yet, somehow, it's still holding on. How? That's the mystery. Some leading theories suggest we've misestimated its distance. and maybe it's not as big as it seems. But new data from the European Space Agency's Gaia mission, measuring stellar parallax and motion, confirms it's right around 19,000 light-years away, meaning our size calculations are probably correct. Others suggest it's not spherical, that it's possibly bloated into a pancake shape, distorted by powerful rotation. This might make it appear larger than it is from our observing angle. Another thing, that it's surrounded by a colossal stellar halo, a kind of cloud or dust shell that extends the visible edge farther than its actual surface. But none of those explanations fully add up, especially when you consider its low average density. It's so diffuse, so loosely packed as a star, that its outermost layers are barely hanging on. By some estimates, Stephenson 2.18's average density is lower than Earth's atmosphere. Think about that for a moment. You're talking about a body millions of kilometers wide. That's somehow less dense than the air you're breathing right now. Almost all of its mass is concentrated toward the core, buried under thousands of layers of glowing gas and plasma, just barely bound by gravity. This is why some scientists propose that massive instabilities could be forming in the outer layers, potential signs of a coming collapse or supernova. And now, here's the part that really breaks the models. Stephenson 2.18 may be shedding mass faster than any other known red hypergiant, yet it still manages to hold shape. The outer atmosphere is so unstable, full of convection cells, solar storms, plasma jets, it's almost alive in its motion. You're looking at something not even halfway into a supernova, and already it's behaving like a star that's in its final death spiral. And that brings us to an uncomfortable question. What if Stephenson 2.18 isn't just a strange exception? What if it's a new kind of object? Something we haven't properly defined, a missing evolutionary stage in stellar life cycles, a brief phase between a hypergiant and a failed supernova? A super-puffed star that challenges the boundary between red giants and gas-cloaked protostars? It wouldn't be the first time we had to update our definitions. Remember, until less than 20 years ago, we didn't fully understand brown dwarfs and we thought pulsars were just noise. We weren't even sure exoplanets existed. Now we've catalogued thousands. Stephenson 2.18 could be another cosmic milestone, a mystery placed right in front of us, glowing faintly through a screen of dust, waiting for someone to crack it wide open. And one last fun twist. We're not even seeing it as it is today. Because it's nearly 19,000 light-years away, we're seeing an image from 19,000 years ago. That's how long its light has taken to reach us, so for all we know, it might have already exploded. Right now, in real time, it could be gone, obliterated in a supernova, obliterating itself and sending shockwaves through space we won't detect for millennia. The largest recorded star might already be dead, and we're just now watching its last breath. At the heart of Stephenson 2.18, a war is being waged. Not a war of guns or bombs, but one of energy. Raw, unrelenting nuclear energy. This star, this impossible giant, is living its final life at full intensity, burning through everything it has just to stay alive. And unlike our sun, which will shine steadily for billions of years, hypergiants like Stephenson 2.18 live fast, burn hot and die young. But it's not just burning hydrogen anymore. No, it's past that. The sun is comfortable, still well within its stable hydrogen fusion phase, slowly turning hydrogen into helium in its core. But for Stephenson 2.18, that phase is ancient history. This monster is already fusing elements beyond hydrogen, elements like helium, carbon, neon, even oxygen. Even oxygen. Each stage of fusion is more intense, more unstable, and more desperate than the last. The star is racing toward collapse, fusing heavier and heavier elements as gravity tries to squeeze the core tighter and tighter. Imagine it like this. A massive star dies like a collapsing building. But not suddenly, floor by floor. First, hydrogen fuses into helium. That stage is relatively stable, lasting about 90% of a star's life. Then comes helium fusing into carbon. That phase burns faster, thousands of years. Then carbon into heavier elements like neon and magnesium. Some of those stages last only years. Eventually, it begins fusing oxygen into silicon and sulfur, and this happens in months or weeks. Finally, in its core, the star will try to fuse iron, and that's when the clock hits zero. Because iron doesn't fuse the way the others do. Fusing iron doesn't release energy. It consumes it. It's like a dead battery. It's the end of the road. When a star starts fusing iron, it's living on borrowed time. In fact, this final stage can last as little as a single day. In that moment, gravity wins. The outward pressure from fusion stops. The core collapses in a fraction of a second, triggering an explosion so powerful it outshines galaxies. That's a core collapse supernova, one of the most violent events in the universe. Now think about this. Stephenson 2.18 may already be simmering in one of these last stages. It could be building iron, dying quietly under billions of kilometers of gas, wrapping its final minutes in a cocoon of stars and dust, and we wouldn't even know because the light from that final explosion hasn't reached us yet. But even before collapse, even before the death blow, the inside of a red hypergiant is a place unlike anything we can truly imagine. Let's take a tour. To reach the core, you travel through layer upon layer, each one churning with fusion reactions. First, a thin, cooler outer layer of hydrogen, constantly blowing off as stellar wind. Deeper down, a convective zone of helium, hot plasma bubbling up in massive shifting cells bigger than entire planets. Beneath that, zones of carbon, neon, and oxygen fusion, each glowing hotter than the last. All of this sitting atop a super-dense core that's building grotesque amounts of iron atoms under a crushing rain of gravity, and every layer is unstable. Every day, those convective zones roar with outbursts, enormous solar flares, shockwaves, plasma jets, giant loops and waves of material firing off into space, all because the star can barely hold itself together. The surface is not calm, not glowing peacefully like art would show. It's chaotic, shredding itself with magnetic storms and ionized particles. In some places, the surface may be hot enough to vaporize entire planets. In others, cooling plasma spirals back inward like waterfalls made of fire. It's poetic chaos, controlled only by the limits of physics, and those limits are being stretched every second. And here's the tragic beauty of it all. These violent last breaths are essential. Everything around you, your bones, your blood, your phone, your microphone, the very earth below your feet, exists because of ancient stars like this one. Stars that died in fire, scattering heavy elements into space. You are made of the same oxygen it's burning, the same metals locked in its heart, the same carbon being fused as we speak. Without stars like Stephenson 2.18, there would be no planets, no life, no people, no you. So when we talk about this star, when we say it's important to understand what it's doing, how it's living, what it's becoming, it's not just an academic exercise, it's personal. Because it's a glimpse into where we came from, and what's waiting to happen all over again. For the only reason we haven't seen it go supernova is because of distance. The light is still travelling. We might not know for another 100 centuries, or it might be tomorrow. And when it happens, when Stephenson 2.18 finally reaches its catastrophic finale, the explosion won't just be loud. It'll rewrite the skyline of that corner of the galaxy. Some astronomers believe the supernova that follows might leave behind not just a neutron star, but something even more extreme, a newly born black hole. Because when a star this massive and this dense finally collapses, not even light can escape what's left behind. That's what we'll look at next. Because the death of Stephenson 2.18 may not be the end of the story, it could be the introduction to something even darker. There's a saying in astronomy: the bigger the star, the faster it burns and the louder it dies, and Stephenson 2.18, the largest star ever discovered, may one day go out with a roar loud enough to shake an entire corner of the galaxy. Because when a star like this reaches the end of its life, when fusion can no longer hold gravity back, the result is nothing short of cataclysmic. It begins with silence. At the center of the star, in the core, fusion has grinded to a halt after burning through every possible element. Hydrogen is long gone. Helium depleted. Carbon, oxygen, neon, all burned. The star has done everything it can to survive, and now fused iron is ticking away at its core like a silent clock. Now gravity is winning. Suddenly, the core implodes, not slowly, instantly. In less than a second, the entire internal structure of the star collapses. If the core had been the size of Earth, it now condenses to the size of a city. Particles are literally crushed together. Protons and electrons forced into becoming neutrons. Temperatures skyrocket. Pressure explodes. Then the outer layers, still incredibly massive, begin to fall inward toward the collapsing center at a quarter of the speed of light. But the core is already too dense. It won't compress any further. The infalling layers slam into the surface of the core and rebound with a titanic explosion. This is the moment the supernova is born. Energy equivalent to 100 octillion nuclear bombs. That's a 1 followed by 29 zeros, erupts outward. In that instant, the entire star is obliterated. We're talking about a blow so bright that if Stephenson 2.18 goes supernova, even from its distance of 19,000 light-years, its light might still be visible to us here on Earth. For weeks, maybe months, so bright we could see it in the daytime. And keep in mind, it would have actually exploded 19,000 years ago. We'd just be seeing it now for the first time. But here's what really stirs the imagination, what's left behind. Because when a star this huge dies, it doesn't just leave behind ash and dust. Sometimes it creates something utterly alien, a neutron star, or worse, a black hole. Let's make sense of how this works. If the remaining core, what's left after the outer layers blast away, is 1.4 to about 3 times the mass of our Sun, you get a neutron star. A city-sized ball of pure neutrons, so dense that a teaspoon of it would weigh several billion tons. It's insane, magnetic, radiating, spinning like a lighthouse in space. But if that leftover core is heavier, over 3 solar masses, gravity has one final terrifying move. Collapse without end. No force in the universe can hold it back. No structure, no physics, no known pressure can resist what happens next. The core collapses into a single point of infinite density, a place where our equations break, where time and space themselves are twisted beyond recognition. A black hole is born, not theoretical, real, a sphere of gravity from which not even light can escape. And there's a real chance, maybe even a certainty, that Stephenson 2.18 will end this way. Its enormous mass and size almost guarantee that when it finally dies, when its final collapse comes, it will leave behind a black hole multiple times the mass of the Sun, curled into a space smaller than a city. Think about that for a moment. No visuals can do it justice. You're talking about a mass thousands of light seconds wide, all vanishing into darkness in a heartbeat. But here's the wild part. Many scientists suspect this process may have already happened. Remember, we observe this star from 19,000 light-years away. That means everything we see is an image frozen in time. The light we get tonight from Stephenson 2.18 left before human civilization even invented farming. It left before cities existed, before the Egyptian pyramids, before the first wheel turned. So if it exploded, we haven't seen it yet. But when the light does get here, if and when it does, it will be more than just a spectacular flash in the sky. It would give us a front-row seat to one of the most powerful events in the universe, the death of the largest known star ever recorded, right before our eyes. And that event would do more than dazzle the sky. It would help scientists test the very limits of physics, from stellar collapse and neutron degeneracy to black hole formation and gravitational wave theory. Observatories around the world would mobilize, radio telescopes would listen, space telescopes would measure, particle detectors would scan the heavens for the faint tremors of new knowledge. Because every massive star that dies gives us clues to everything from how galaxies evolve, to where life gets its chemistry, to what happens inside the fabric of time and space itself. And this time, those clues would be born from a celestial giant unlike anything we've seen before. Stephenson 2.18 would leave behind a legacy, not just of size, but of transformation. For now, we wait, we observe, and we wonder. Because the future light of this massive star's death may already be on its way across the universe, reaching toward us from the distant past. And if it ever arrives, we won't just be witnessing the end of a star. We'll be witnessing a message from 19,000 years ago, finally arriving at our door. For all the numbers, models, simulations, and careful measurements, there's still one uncomfortable truth about Stephenson 2.18 that scientists have to face. We don't really understand it. Not completely. Sure, we've taken its infrared measurements, we've estimated its radius, we've calculated its luminosity, its temperature, its chemical makeup. But even after all that, Something about this enormous bloated star simply refuses to sit properly inside the neat boxes of astrophysics. It's as if the universe itself whispered, "You thought you had it figured out," and then dropped this monster of a star right in the middle of our Milky Way, daring us to explain it. And that's opened the door to wild, fascinating, and sometimes deeply unsettling theories. Let's explore a few of them. First up, the idea that Stephenson 2.18 is not just a star, but a symptom of something bigger. There are researchers who believe this hypergiant might be interacting with, or revealing, signs of dark matter. Now, dark matter is one of the universe's greatest mysteries. It's invisible. It doesn't emit or reflect light. We can't see it, touch it, or detect it directly, but we know it's there because of its gravity. It's like seeing trees bend in the wind even though you can't see the air moving. In fact, over 80% of the matter in the universe may be dark matter. This strange, untouchable substance that we barely understand. It surrounds galaxies, shapes clusters, and possibly weaves through all of space in a giant cosmic web. Now here's the twist. Some theorists propose that stars located in dark matter, rich regions of the galaxy, especially massive stars like Stephenson 2.18, could be subtly influenced by it. How? There are several possibilities. Maybe streams of dark matter are interacting with the core, ever so slightly altering its fusion rate or gravitational behavior. Or maybe it's affecting the mass loss process, preventing the star from shedding material as quickly as it should. Or perhaps Stephenson 2.18 formed in a region of space where the density of dark matter was high enough to influence how it evolved, explaining why it reached such an impossible size. We don't know. And that very ambiguity is part of what makes Stephenson 2.18 so important. Because we need stars like this, anomalies, to test our limits. In physics, breakthroughs don't usually happen during quiet, predictable events. They happen when something doesn't fit, something sticks out, something shouldn't exist, but does anyway. And Stephenson 2.18 might be the cosmic outlier pointing us toward a new understanding of reality itself. Another theory, a little more controversial but no less thought-provoking, is the idea of exotic matter or alternative gravity models. Some physicists suspect that in extreme environments, like the cores of hypermassive stars, the normal rules of gravity may not behave exactly as we expect. Could Stephenson 2.18 be a testing ground for modifications of Einstein's general relativity? Maybe there are small deviations in how mass interacts with space-time under extreme scale. Maybe gravitational leakage is happening, or additional unseen forces are balancing the star's structure in unknown ways. These theories remain speculative, but they point to one essential truth we can't ignore. The universe is stranger than we think, and sometimes observing a single incredible object, like this star, gives us more insight than decades of computer simulations. There are even fringe theories that wonder if Stephenson 2.18 could be an entire stellar system hiding in plain sight. Multiple stars so closely bound by gravity that their light and mass combine into one object, mimicking a hypergiant. Or that the star is surrounded by a cocoon of matter left over from its formation, which we're wrongly including in its measured size. Of course, most observational data suggests it really is a single star, one so massive and extended, its density approaches fog levels and its edges might not even be clearly defined. But that in itself raises more questions. Is there a point where a star becomes too diffuse to be considered a true star at all? Are we entering a new category of stellar object, something between a star and a dying gas giant, barely held together by its own fading gravity? The truth is, we don't know. And that's why Stephenson 2.18 creates such a buzz in the scientific world. It's enormous, it's strange, it's unique, and somewhere inside its glowing radius, there may be answers to some of the deepest questions in modern science. What is dark matter, really? Are there forms of matter or energy we haven't discovered? Are we missing something crucial about gravity? Are there forces acting on stars that we have yet to detect? Stephenson 2.18 sits in that mysterious, awe-inspiring zone where science and mystery overlap, where everything we think we know starts to blur at the edges, because in the end, the beauty of space isn't just what it shows us, it's what it hides. And Stephenson 2.18 might just be hiding far more than light and gas. Let's ask a dangerous question. What if we're not the only ones looking at Stephenson 218? We've spent the past chapters exploring size, gravity, fusion, and death, trying to understand this star through the lens of physics. But maybe there's another lens just as important: imagination, because whenever we discover something this colossal, this extreme, something perched at the very edge of what physics can explain, it's hard not to wonder, are we the only ones watching? Just think. For hundreds of millions of years, Stephenson 218 has blazed quietly in the distant sky. Long before humans ever existed, it was already burning, and long after we're gone, it may still be remembered, not just by us, but by something else, somewhere else, somewhere else. For thousands of years, people have looked up and wondered if anyone is looking back. Now, with modern science, that question carries a little more weight. Because the bigger and weirder an object is, the more attention it draws, right? Here on Earth, observatories, telescopes and engineers have worked tirelessly to detect, chart and model this hypergiant. It's hidden in dense stellar fog, it's inaccessible to the naked eye, and yet we found it. So if we found it 19,000 light-years away, then what's stopping someone else out there from finding it too? And that leads to one of the most fascinating ideas in astrobiology and SETI, the search for extraterrestrial intelligence. It's the idea that not only might there be life out there, but advanced life. Civilizations developed enough to study the galaxy just like we do, maybe even millions of years ahead of us, with senses beyond anything we've imagined. Would they notice Stephenson 218? Almost certainly. Think about it. Even for a galactic civilization, a star like this would be hard to ignore. Its size, its infrared output, its instability, its uniqueness, it's the kind of celestial landmark that would stand out in any survey of the Milky Way. So perhaps they're studying it too. Not for fun, but for data. Maybe, just like us, they're trying to understand how stars live and die. Maybe they track hypergiants like we track hurricanes. Maybe they have probes in the region orbiting quietly, waiting to feel when this massive star finally collapses. And maybe, just maybe, some civilizations look at stars like Stephenson 218 as energy sources. This brings us to one of the boldest ideas ever proposed in astronomy, the Kardashev scale and the concept of stellar civilizations. In short, the categorizes civilizations based on the amount of energy they can harness. Type I civilizations use all the energy on their home planet. Type II civilizations capture the energy of an entire star. Type third, they wield the power of an entire galaxy. Now, we're not even fully Type I yet, but what about someone who is Type II? A civilization like that might build structures to harvest the energy of stars, something like a Dyson sphere or a Dyson swarm, vast layers or fleets of solar collectors orbiting a star, soaking up its power to drive their machines, technology, or even their environments. Could a star like Stephenson 218 be used this way? Theoretically, yes. If not enveloped completely, then at least closely monitored. Maybe they wouldn't build around it. It's far too unstable. But they might drop observation buoys around it, place gravitational wave sensors, or harvest material ejected from its surface. Every pulse, every flare, every loss of mass would be a signal, a forecast of a future cosmic event. And for a civilization with the time and patience, watching this star would be like watching the clock on a cosmic bomb. There are even sci-fi theories, the kind whispered about in the halls of theoretical physics, that massive stars could someday be used as beacons. Imagine this: a civilization encodes information in stellar modulation, tinkering subtly with the light, the radiation, or the plasma bursts of a star, embedding data like cosmic Morse code. Now, before you dismiss it, remember, we already encode information in radio waves and lasers. It's the same principle, just on a far grander scale. Could anyone be doing that with Stephenson 218? Probably not. But we don't know, because here's the truth: we haven't been looking long enough or clearly enough to answer. Space is vast, the star is dim, and the universe doesn't give up all its secrets on the first try. So for now, we watch, not just for answers but for patterns. Because even in the deepest, emptiest parts of the galaxy, information can travel, light carries it, radiation broadcasts it, and sometimes a star itself becomes the message. And here's something beautiful to ponder: if someone out there is watching Stephenson 218 too, Then across the gulf of 19,000 light-years through a silent ocean of dust and cosmic storms, we are sharing a moment with them. Different skies, different worlds, different forms of life entirely maybe, but the same star. That alone is enough to make you feel less alone in the universe. Maybe we haven't made contact yet, but this is contact of a different kind. Because in a galaxy of 100 billion stars, even just one, if it's big enough, strange enough, mysterious enough, can get two civilizations to look up at the same time, wondering the same thing. And when it comes to mystery, Stephenson 2:18 delivers every time. Every so often, a single discovery changes our direction. Not just in science, but in how we understand everything. Our place in the cosmos, the limits of matter, even the boundaries of imagination. Stephenson 2:18 is one of those discoveries. And the deeper we investigate it, the clearer it becomes. This star isn't just a marvel, it's a message, a challenge, one that dares humanity to look beyond what we thought we knew and ask bigger questions. Because here's the truth, this star is teaching us. In its unimaginable scale, in its slow collapse, and in its defiance of theoretical models, Stephenson 2:18 is forcing astronomers to revise what they thought was settled science. For decades, astrophysicists have worked with equations that predict how stars live, burn, expand, and die. Those models work beautifully for stars like the Sun, even for giants like Betelgeuse or Antares. But Stephenson 2:18, it casually strolls outside the bounds of those rules. It's like someone dropped a puzzle piece from another game onto the table and said, "Oh, figure this out." Studying it has already pushed fields like stellar physics, infrared astronomy, and astrodynamics forward. Entire new methods of scanning and measuring deep sky objects have been developed just to better understand this one single star burning in the fog of dust 19,000 light-years away. And here's why that matters. Every time we study something that shouldn't exist, we learn something new about existence itself. Stephenson 2:18 has shown scientists that the math we had may not be enough. It's reminded us that the universe doesn't have to play by our rules, it just has to be. Reality is under no obligation to match our simulations, and often it doesn't. And yet, rather than being discouraged by this, scientists are thrilled. That's the beautiful paradox of discovery. The confusing things are often the most valuable things, because they force us to think hard. Look deeper. Expand further. In tracking and analysing Stephenson 2:18, we've sharpened more than our instruments, we've sharpened our curiosity. New satellite missions only became priorities because of stars like this. The James Webb Space Telescope's capacity for infrared observation can finally drill into dusty stellar fields like never before. Future arrays like the Square Kilometre Array and other deep space radio observatories might one day listen for changes coming from stars like Stephenson 2:18, long before human eyes can detect them. Even computer modelling has improved. Simulations of red supergiant interiors are becoming far more advanced, thanks to the mysterious inconsistencies stars like 2:18 have revealed. We've realised that a star's boundary, a solid surface, may not be as clear-cut as we thought. And that density, mass and stability may not always correlate the way textbooks once said. We've also learned something powerful about scale. Ask the average person how big a star can be, and most will think of the Sun, maybe a star a few times larger, like Sirius or Vega. But then you're introduced to Stephenson 2:18, and suddenly the numbers start breaking your intuition. Gravity, density, fusion, time all feel different inside its gravitational presence. We're talking about a star so immense that light needs 8 hours to cross it. One so large that its surface is so spread out, so fog-like in density, that it blurs the line between star and space. That kind of size alters how we think, not just in science, but in philosophy. We are small, unbelievably small. And yet, we can still find, observe, and try to understand something as titanic as Stephenson 2:18. That tension between our insignificance and our intellect is what makes this study so important. The fact that we can even ask the right questions speaks volumes about how far we've come. But these aren't just questions for scientists in observatories. They ripple outward into education, creativity, culture. Children seeing the star's light curve graph in a classroom today might be the ones who build the observatory that watches its death flare tomorrow. Artists, writers, filmmakers, they now have new symbols of size, power, and beauty to use in their stories. Engineers dream up better ways to measure the impossible because stars like this demand it. In short, Stephenson 2:18 makes us better, even if we never fully understand it. It humbles us, inspires us, and demands we keep reaching. And that's more than just scientific value. It's human value, because no matter how big the universe is, no matter how massive the stars get, it still means something that somewhere on a floating rock in the corner of a galaxy, a thinking mind looked up and noticed. For all the science we've explored, all the numbers crunched. For every light year measured, for every fusion cycle discussed, there's one last truth we can't ignore. This is more than just a star. Stephenson 2:18 is a symbol, a cosmic monument to scale, to mystery, to beauty and wonder. It's one of the most extreme things we've ever found in the observable universe, yet its story is ultimately human, because hearing about something this enormous doesn't just make your brain light up, it touches something older, something deeper. It reminds us of why we started looking up in the first place. Before math, before telescopes, before we could measure or name anything, people stared into the night sky and wondered what was out there. We told stories about the stars, shaped myths around them, built temples aligned with their rising and setting. We may not have known the chemistry or the physics or the lifespans of stars like Stephenson 2:18, but we felt it, that the sky meant something. We sensed there was something bigger than us, older, more enduring, something powerful. And now, here we are, in the age of infrared observatories and gravitational wave detectors, finally giving names and data to the giants we once worshipped as gods, and yet the feeling is the same. That mixture of awe, fear, and curiosity you feel when you try to imagine it. That's not science fiction. That's perspective, the kind that comes only from standing at the edge of the known and peering into the unknown. Because even now, we don't know how long Stephenson 2:18 will last. It might already be gone, a black hole silently born in a collapsed corner of the galaxy whose light hasn't reached us yet. Or it might still be out there, still bleeding mass, still swelling, still burning for thousands more years before the final collapse. From our point of view, from this pale blue dot orbiting an ordinary yellow star, we are witnessing a massive dying ember at the far horizon of the galaxy. And just the fact that we know that, just the fact we found it, measured it, named it, is enough to justify everything we've ever done to learn more about space. Because when we study the impossible, we become more than just observers. We become participants in the grand story of the universe. We add our chapter, and maybe thousands of years from now, long after Earth has changed, someone will look back from a ship, from a colony, from another star system, and remember that there was once a star so big it redefined what humanity thought was possible. They'll say it lived in the hidden fog of dust, 19,000 light-years away, that its light stretched across entire planetary orbits, and that once upon a time, a civilization of thinkers tried to understand it. And maybe they'll smile and say, a Stephenson 2:18. That was the one that made them question everything. That was the one that opened the door to more. Not just a star, a landmark, a cosmic moment frozen in light. Right now, its glow is still travelling through the galaxy. Somewhere beyond us, its photons are racing past other star systems, other planets, maybe even other civilizations. And maybe, just maybe, when they look up and see its glowing signature, they'll wonder, who else saw this first? Who else dreamed about it? And our story will be there. Drifting through space, tied forever to a giant that once hung in the dark, earning our questions, our wonder and our respect. So to Stephenson 2:18 we say this, you shouldn't exist, but we're so glad that you do, and while you still burn, we'll keep watching, because in your light we see farther Vidni. In your mystery we reach higher, and in your colossally impossible existence we remember why we search the stars.